Sindy. Sindy is from our China company, Tensar Geosynthetics China. And what'll be very nice is you're going to see a wide range of applications of reinforced soil slopes in many situations and conditions. And I think by now Cindy will probably show you 7 or 8 of these in her presentation, but they cover quite a wide time range. They go back over 20 years, the very earliest ones, and also many different situations and many different applications, for example, in highways, in rail, in repairing failures. Anyhow, you'll learn more about that when Cindy starts to talk to you shortly. So let's look at some pictures of reinforced soil slopes. Some of these are from China, some of them aren't, but I think you get the idea. This is a very tall structure, and you can see them building it at the top there. This one, I think, had an overall height of probably about 30 meters. It's quite big. And then after completion, it looks like this. So one rather nice thing about reinforced soil slopes is that normally they are covered in vegetation, very much like this one when it's finished. So the nice thing about vegetation, of course, is it absorbs carbon dioxide. So although you will expend or you will put carbon dioxide into the atmosphere when you construct them, when they have their lifetime after that, they will, in general, over their lifetime, absorb much more carbon than was emitted. So here's another one. This is actually a project in Malaysia. This was the repair of a slope. So it's a lower angle structure. The other one was very steep. But these are all reinforced soil slopes. This one is actually in China. I'm not going to tell you any more about this one, except that this is a before picture, and this is one when it's a bit more established. Cindy will tell you much more about that project shortly, but you just got some idea about what these structures look like. So I just want to cover two main, yeah?
Sorry, Mike, we can't see your slides.
At all?
Yeah, we can only see the slides, just the ICE image.
Right, so you haven't seen anything yet?
Yeah, it's just a slide of the introduction of ICE Jakarta and your name on it.
Thank you for telling me that. I'd have been going on assuming that people were watching the slides. Okay, let me just try and find out what's going wrong there because I shared my screen. I'll do it again.
Mike, I think it said we were seeing operator two's screen.
Oh, thanks, Chris. Hang on, let me see if we can try this again. Are you seeing a screen with basically some?
Yeah.
Yeah, that's better. That's a.
Okay, right. In that case, I can shut that down. I hope I'm now back in the meeting. I'm afraid it got cut off. Can people hear me?
Yes, yes,
Oh,
clear now.
okay. Sorry, let's start again then. So let me share screen now and make sure we do this properly. Right. So I'm sure you can see that. So I will start. So, okay. So I hadn't got very far. I hope you can see my slides now. Um, so I mentioned that the presentation will be in two parts. So I'm going to provide some background information, and then Cindy will tell you about experience from China. I've already been through that. I showed some pictures which actually are quite nice, so I'll just show them to you again. We can see them properly now. Just examples of reinforced soil slopes. These are quite big ones, most of them. This one you can see being built with a series of tiers, and that's during construction, and that's the same slope after completion. And I mentioned the issue about vegetation, how we get this benefit that reinforced soil slopes, generally they're covered in vegetation, which means that generally they are being very friendly to the environment. And the one in this is a low angle slope repair in Malaysia. But again, you can see it's the bit right in the middle of the picture, how it's blended in with the general background. And this is the one from China, which Cindy will talk about a little bit later on. So I think that's as far as I've got. So I want to talk about two things. I want to talk briefly about input parameters that we require to make these designs. And then after that, just a few words about the design of reinforced soil slopes. You'll see the practical results of this in Cindy's presentation, but I'm just going to provide you with some background information. So first of all, input parameters. This is a very helpful picture that, in fact, I will just activate my laser pointer. So this is a rather nice little picture of a reinforced soil structure, but it's a slope in this case. But you see the principles quite well. Of course, the brown material is soil, and these grid-like images are the layers of geogrid. And then in this case, the facing is vegetation. So it's a very simple technique. And the main purpose of the geogrid, of course, is to stabilize the soil mass. That's what we put it in there for, to give you a stable soil mass, and that's done through calculation. So we have an engineered structure, even though it looks like a fairly natural slope by the time it's finished. It is a properly designed and engineered structure. The advantage of using these are polymer geogrids. An advantage of that is that we can use a very wide range of fill types. So most certainly, generally with slopes, we don't normally import expensive fills to a site. We would normally use the fills already available on the site, which is another one of the nice benefits that we get from these techniques. And also quite a wide range of finishing, the facing, but normally it'll be with some kind of vegetation to make it blend in with the environment. Generally, well, one definition for slopes is that they have a facing angle of 70 degrees or less to the horizontal. That appears in quite a few codes of practice. And it does make sense in some ways, because generally design approaches will be slightly different. And also at this angle, we can start to use vegetation. So I said that normally with vegetation, that particular one built a long time ago, well over 30 years ago in Hong Kong, and still doing a very nice job today. Here is a fairly steep structure. This is built using what's the wraparound we saw just now. That one also well established in a project in Brunei, built many years ago. We can also use different forms of wire mesh basket. If a wire mesh is considered to be a more satisfactory facing, then that can be combined also with vegetation, and that's what we see in this picture. In this case, the mesh panel at the front is joined to the geogrid by a positive connection. One type of facing, or one type of structural item quite well known here is the gabion or bronjong. They can be used as facing as well, And when we do that, we only really use a thickness of 1 gabion. Normally, for a tall structure like that, you need a big depth of gabions to build it as a gravity retaining wall, but that would not be the case here. So we can just use geogrids combined with gabions to form a structure. When we go down to structures below 45 degrees, then we don't really need any facing as such. We can simply finish off the soil and then grow vegetation. Sometimes people might combine that with some kind of erosion control mat. So that's the case on this one. That's about a 45-degree slope, and it's just been stabilized on the surface only with a vegetation control mat. So that's what they look like. So just a few more words about input parameters. We've talked about the facing systems. What do we need in the way of soil parameters? Well, if we have a cross-section of a reinforced soil slope here, of course, we need to know its dimensions. That's an important part of the input and any surcharges it must carry. And then, of course, we need to know the properties of the fills. And these will be given in terms of a C dash and phi dash and a unit weight. And of course, if there's any water involved, any water levels or water pressures expected, they need to be taken into account as well. And just to make an important point, the design method I'm going to mention in a minute assumes a competent foundation. There are 2 design methods I'll briefly mention. So to look at the actual effect of the foundation, we need to do some further analysis, which I'll come to a little bit later on. When it comes to fills, either reinforced fill or backfill, then we will use what are called the drained soil parameters, or the parameters in terms of effective stress. That's C dash and phi dash. And that'll be for all soil types, whether it's a clay fill or a granular fill, then we will use those parameters to design the structure. We would never use undrained shear strength within the reinforced soil mass. But when it comes to the foundation level, then if we have granular foundation materials, we'd normally use drain parameters. But if we had clays or cohesive soils, we would generally use the undrained shear strength in the foundation. So just moving on. So back to our cross section. When it comes to the reinforcement, then there are certain design conditions that will affect the strength of reinforcement, in particular the design life, also the design temperature, and the maximum particle size. And I'll just explain to you a little bit about that in the next few images. So here's some polymer geogrids laid out. This is actually behind a retaining wall, but they would look much the same if they were being laid out behind an inclined facing of a slope. We call these uniaxial geogrids because they have a high strength in just the one direction. That's to say the direction from left to right in that picture. These are polymer geogrids. These particular ones are monolithic. They are solid polymer. There are no fibers or coatings. They're just a solid piece of polymer. And when we design with them, we need to use a design strength, an allowable long-term strength, TA, in that formula. And this could be calculated from a number of different formulae, but they depending on the codes or standards you're looking at, but they all have essentially the same approach. So what happens is we have a tensile strength of the geogrid, T ultimate, and then we reduce it by a number of different factors to take into account what is called creep, which is the long-term behavior of polymers, any installation damage, and also, of course, very importantly, durability, to take into account of any chemical or environmental effects that might affect the strength of the geogrid. Now, how do we find these things? Well, we simply have to do lots of testing. So today, just very briefly, to show you what the tests look like, this is a tensile test to measure its short-term tensile strength. We then have special laboratories called creep laboratories, where we hang up samples and we put weights on the bottom and we measure the strain over time. And from that, we can interpret the long-term strength. And we do this at different temperatures to take into account both different environments and to give a technique for extrapolation of the data. So for today, just one simple picture about that, but it's quite a long story, the whole the whole description of how creep testing works. So today, no time. Then we also want to find out the effect of compacting aggregates or fills on top of geogrids. So we do that in a very simple way. We lay them out on a site, we put fill on top, we then compact them, and then we carefully excavate and remove them and see the effect of that process on their strength. And from that, we get this RFID, which is a reduction factor to take into account what we call installation damage. And then the third main category was to do with durability, RFD. And that this is a very long story, but a very, very important one. But we need to look at things like weathering, which is the effect of weather. In other words, exposure to high temperatures and rain and so forth. Oxidation, which tends to affect what's called the polyolefins like HDPE and polypropylene. But also then there's resistance to liquids, especially of high and low pH, where it's many of the polyester geogrids which we need to look at that, particularly from the point of view of what's called hydrolysis. So RFD, a very important parameter to include in the assessment of the geogrids. So back to our cross-section, what else do we need to know? We need to know what are called interaction factors, because when we combine geogrid and fill, then there is an interaction between them. And in fact, the next picture shows it rather nicely. You can see there a piece of geogrid buried in fill, and you can see that obviously the quality of the interaction is extremely good. But of course, we need to measure what that is, and there are two types of interaction that affect our designs, the sliding and pull-out. So how do we measure those? Well, to look at sliding, we simply use what's called a large shear box, and we put geogrid at the central point, and we simply shear the soil across the geogrid in the middle of the shear box. It's a fairly obvious test procedure, but that's how we do that. And then the other main type of interaction we want to look at is pull out. That requires rather larger apparatus where we bury geogrids in a fill. So that's you can see that's the geogrid resting there on one layer of fill, and then more fill goes on the top. And then we apply a normal force on the top of the whole thing. And then we go around to the right-hand side of that apparatus and pull on the geogrid until it fails. So that's how we determine pull-out interaction. Now, these various parameters all go into the design calculations, all the ones I've been talking about: soil properties, geogrid properties, and interaction. Now, if you're interested in and think, well, it's rather important to have some kind of independent verification for any particular geogrid I might be looking at, then I'd recommend strongly a good source of this are what are called BBA certificates. These are certificates issued for the materials themselves in certain applications. So in this case, the one over here on the right is for what they call reinforced soil embankments. And these are available for many, although it says Tensar geogrids, which are the ones that we manufacture, this is available for many, many geogrids. It's a very, very, very good source of information if you're considering using these materials to design structures. So BBA certificates, the only thing you need to be aware of is that they are published for the conditions of the UK, which is rather colder than Indonesia. So you need to make sure that the effect of higher temperatures is taken into account when you assess the long-term strengths. Okay, so that was input parameters very briefly. Now just a few words about designing reinforced soil slopes before Sindy shows you the actual practical result of doing this. And I'll just briefly look at three things. I'll look at what are called chart design methods, and then a few words about an analytical two-part wedge method, and then a summary with the full design process that you should follow when you're designing structures like this. So here is again our cross section. We got to this stage just now. That's for a low angle 45-degree slope, but of course you could be looking also at a steeper slope like this, a 65-degree slope. In this case, you would use some kind of facing like a wraparound that we saw earlier on. The design procedures are essentially the same for both forms of structure. And in fact, one very nice way to get an idea about how they differ from each other, from different facing angles, is to look at design charts. Now, these charts, published by Schmertmann a long time ago. You can see 1987. But that doesn't mean there's anything wrong with them. In fact, they are very, very useful ways of getting a first indication of what you require in terms of dimensions and so forth for your reinforced soil structure. Let me explain briefly how they work. So there are two charts. The horizontal axis is the slope angle you want to design in both cases. And the right-hand chart gives what's called a force coefficient. But essentially, it's a measure of the total amount of force you need to resist in your design. You take into account, of course, the height, and it's a little bit like a kind of active earth pressure coefficient. But and the other chart is for the length of the reinforcement compared to the height of the structure. So let's have a quick look at that. And I'm just going to do this for two phi values. For one phi value and two slope angles. So we'll look at a phi angle of 31 degrees. Now, if you use these charts, you need to apply your safety factor at this stage. So I apply it to the tangent of 31, and I find I have a design phi value of 25 degrees, which takes into account the required safety factor that we need. Having got that, how do we then use the charts? Well, let's look first of all at the force coefficient. And we've got those two angles, 45 and 65. And when you read up here, you will see that for this green line, which unfortunately is hidden behind here, but that green line is the line for 25, phi equals 25 degrees. Then we have a certain force coefficient. And what you'll notice, it doesn't really matter too much what the actual number is, but what you'll see is for the steeper structure, we need almost double the amount of reinforcement resistance compared to the 45-degree one. So this has a big effect. The facing angle has a very big effect in your design calculations. The other chart is for the length. So if I, again, add some lines for 65 degrees and 45 degrees, then you can see that we have a certain length here, which is around about 0.7 or so of the height. So if the height was 10 meters, length of geogrid would be 7 meters. When you come to lower angle slopes, there are two lines. The line for the base, which is actually a bit longer, it's about 0.8, but also the second one is for the top. So for low angle structures, it's sometimes more efficient to change the length of the reinforcement and have it differing from the base, in this case, which would be longer, up to the top, which would be shorter. That works quite well for low angle slopes, but there's almost no point in doing that for high angle slopes. There is an analytical method which is quite good called a two-part wedge method that was based on a particular design guideline coming from the UK Highways Agency, which is officially withdrawn now, but nothing wrong with it. But this gives you a design procedure, again, for steep slopes with facing angle less than 70 degrees, and it's based on a two-part wedge method. Rather like the charts just now, it's for a single soil type, so you've only got one phi value you can use, and the foundation assumed to be competent. I'm not going to run through the details at all, just to show you a picture of it. So what you would do, you would use this two-part wedge, you'd analyze the forces involved, and you would use that to find out what is the length of the reinforcement and the required resistance. Again, that's quite a long description all by itself, not enough time today. But how do we do this? How do we put it all together? So let's just go to an image from a computer program. It happens to be one that Tensar make, but there are other forms of program like this. But if we want to design that particular structure, which is in this case you can see it's a 9-meter high slope, we can use the two-part wedge method. We put in all the parameters, we run the procedure, and at the end of all that, we end up with a layout of reinforcement which is satisfactory. But just to remind you, one slight restriction, if you like, of that procedure was that we only have one soil type, and it's assumed that the foundation is competent. So what we then want to do is to take that layout and we'll put it into what's called a slope stability program like this, and then we can change the the geometry. If the realistic situation looks something like this, we can change all that. We can't do that in the previous program, but in a slope stability program we can. And then having done that, we can then run our analyses to look at the stability of this structure. So just to give you some idea, I'm just going to shrink it down a bit and run a circular analysis on this, which we do with a rather clever technique. And what this does, it hunts until it finds the lowest safety factor by looking at lots of different possible circles. And at the end of that, we get a final calculation of a safety factor. The minimum value down the bottom here is actually 1.38, which would normally be satisfactory. So that's allowed us then to design that slope. Why is it quite nice to start with the simple methods? Because if you want to design this slope using only stability analysis, there's a lot of trial and error to use. So the initial design method, like the chart, gives you an initial layout very easily, and then you can check it with stability analysis. So we've looked at information about input parameters for designing these slopes, and I've also taken you very briefly through both chart-based and analytical methods, and then we've looked at the overall process of doing it, where you need to do final checks using either LEA or FEA just to check that your overall design is satisfactory. So I've gone way past the time I meant to take up, partly because of the slight problem at the beginning. But I now want to introduce my colleague Sindy to you. Sindy has been my colleague for quite a lot more than 20 years now. Before she joined Tensar, she was a highway engineer, so she has good background in that field. But now for more than 20 years, she's worked for Tensar, where she's had a number of roles. But initially, she started as the design engineer, and then she built up a design department, and then she's led that design department, which she still does today. By now this is a very busy design department. I think now with at least 4 people in it plus Sindy. So this group is doing designs of structures throughout China. Sindy also has another job to do in Tensar. She's also in charge of our marketing department in China, which is another job she takes on. So she's pretty busy. However, we're very fortunate she's found time today to tell us something about her experience for designing reinforced soil slopes in China. So it's high time I finished. So I'll just say thank you. We'll invite questions at the end, but I hope most of your questions will be on the material that Sindy will present rather than mine. But you're welcome to try to ask questions about any of them. So I will stop sharing and ask Sindy to take over.
Okay, thanks, Mike. Thanks for your kind introduction. And good evening, everyone. This is Sindy from Beijing, China. It's my pleasure to have this chance to introduce the reinforced soil slope experience to you. The reinforced soil structure were widely used in China in the past 20 years. They were in different provinces with different environments. Our finished reinforced slope number is nearly 200. The maximum height is about 40 meters. The wraparound facing, just as Mike has introduced, this facing is a favorite facing system due to the lower cost. But in general, the wraparound facing is commonly used in South China, where it is most suitable for the grass growing. Recently, we also use the steel mesh panel as a slope facing. We seldom use a high-quality gravel as a slope fill, and the site-owned soil were commonly used, even the clay soil. But sometimes we will ask to mix with some stones or gravels. Regarding the design, we use the slope stability software a lot in the daily work. Normally, we check using the Bishop circular stability method. But sometimes we also need to check the long circular stability when there is some special geometry or soil layer. You may know that China has many seismic areas, so there are many slopes which were built in this area with different seismic acceleration. So today, I want to share with you 10 cases with different characters. The first project is the third phase of the Beijing to Chengde Highway project. It was built just 1 year before the Beijing Olympic Games in 2008. It goes through the mountainous area in North Beijing. The total length is about 63 kilometers, 4 lanes, and the design speed is 80 to 100 kilometers per hour. The highway goes through the several ecological protection areas, so the environmental requirements are very high. The owner just wants to see all in green when driving on the highway, so the traditional masonry and the concrete wall or slope are not capable. In this case, the reinforced soil slope application is accepted. So finally, for this project, we have designed and built 13 reinforced soil slopes. The main challenge are the limited land in the mountainous area and the environmental requirements of grading. You may know Beijing is in the north part of China. The climate is too dry for the plant growing, so we need to consider carefully about the slope angle, the construction method, the plant choosing, and the maintenance. The complex topography and the geology is also a problem. Even for one structure, we also need to calculate several sections. For some structure, we need to use the explosive stones from the tunnel construction as a fill. So we have to do some site installation damage test to confirm the installation damage factor, that is the ID factor. Most of our structures are connected to different type of bridges or tunnels, so that the connection details are also important. These are some design sections. For the structures in the mountainous area, the important thing is you modify the clearly of the existing ground level. In this project, the foundation geology is similar, but the mountainous terrain is so different, even it's only 20 meters apart. These are some detailed drawings for this for different sections. You can find we have provided a lot of solutions for this structure. One thing I just want to mention is the geogrid layout. The arrangement of the geogrid from the design software may be different from the actual layout due to the complex terrain. That means the different existing ground level and the backslope may affect the geogrid length and the level. You should check the stability again when you change the layout from the software. Look at this picture. First, we need to find out the geometry of the structure, the height, and the possible face angle. Then, looking at the field, the site-owned soil is a mixture of the big gravels and sandy soil. So we asked for soil tests and got the confirmation of the final parameters for design. Next, we will consider the drainage, not only the water from the backslope, but also the water from the highway above. In general, the mountain roads have relatively large longitude and transverse gradient. Sometimes the pavement designer only consider to discharge the water out of the pavement. The water may drain out through the structure underneath. It's not a big problem for the traditional masonry or concrete wall or slope, but for the reinforced soil structure, we need to consider whether the discharged water from the pavement will affect the facing of the reinforced soil structure. And the seismic effect is also important, especially for the structures which is located on the slopes. We have checked the stability for all sections under the seismic load. One interesting thing is the client asked for the site damage test. Although we have provided our ID factor for Unix geogrades, but the client still worried about the explosive gravels from the tunnel construction, which are very sharp and hard. So they organized the test to just follow the simple procedure described in BS 8006. The picture shows the sharp granite coming from the tunnel construction. It was placed on the geogrades, and the roller compacts back and forth. After compaction, the geogrades were taken out carefully and sent to the laboratory for a tensile test. Then we got the confirmed ID factor based on the actual situation on site. This is the second section of the project. It's an approach road to the bridge and is 20 meters high, and the face angle is 60 degrees. There is no space for a cone slope at the end of the abutment. So a curved retaining wall is designed to connect the abutment and the reinforced slope. This kind of slope is suitable for the intersection of the complex terrain and the structure. This is the ninth section of the project. We use small steps on the slope to form the slope facing. On the one hand, it's easy to control the construction quality, and on the other hand, it's conducive to retaining the water and facilitating the growth of the plants on the slope facing, especially in the dry climate. The 13th section of the project, now you can see the slope, which is 38 meters high at the connection point to the bridge. The back slope is a steep hard rock, so we reduce the geograde length at the bottom part. The face angle is about 60 degrees. The design section is also showing here. In Beijing, after the cold and dry winter, just 1 year later, the facing is in green in summer. And another slope in the 13th section with a height of 27 meters. It's a 3-tier slope, and the face angle is also the 60 degrees. 3 years later, the wraparound geogrades and the bags were all covered with by the vegetations. The client is very satisfied with the appearance of the slope. These are some other different structures in different seasons in this highway project. All of the reinforced slopes were taken as the embankment to support the highway from Beijing to Chengde. The reinforced soil slope is suitable for the structures in the mountainous area. It's flexible, so it can adapt to the varied topography and geology of the mountains. Another important thing is the guardrail. In general, the high slopes in highway project will use the concrete guardrail. That means a wide and thick concrete foot will be set on the top of the reinforced slope. That's very expensive and will add an extra load on the top. So the client wants to choose the steel barrier, but they still worried about the safety of the slope if there is a car hits the guardrail. So they conducted a full-scale trial. That is very interesting. They built a full-scale slope which is just 1.5 meters high. The face angle is also 60 degrees. It's the same as the real slope. The slope was reinforced by the Unix geograde with 500 millimeters of spacing. The geogrades wrap around the backs and connected to the upper geogrades using the bodkin. On the top of the reinforced slope, there is 500 millimeters of the flash cement stabilized base layer, which is the same as the real pavement. The steel guardrail were installed. It is 2.15 meters high and was driven 1.4 meters into the slope, which followed the standard. And they conduct a vehicle crash test in accordance with the standard. The vehicle weighted nearly 9 tons. It crashed into the guardrail at a specified angle with a specified speed, which is 65 kilometers per hour. They use a high-speed camera to record the test. After the test, the slope seems to have no movement. Some steel guardrail moved, but only a small amount, except where the steel guardrail was driven. The other geogrids were no damaged and deformed. So finally, the steel guardrail was used on the top of the reinforced slope and saved a lot of money in this project. The second case is the Dulong mining project, which is in Yunnan province. The natural mountain slope is nearly 90 meters high. The client didn't choose the original plan, which is the very big slope plus the concrete wall at the bottom. They accepted the reinforced soil solution due to the lower cost and the limited land using. The solution is a 30-meter high structure, including a 10-meter high retaining wall at the bottom and a 20-meter high slope at the top. There is a tailing pond at the end of the slope, so we need to consider the changing water level. The terrain of the site is complex. There is gully, big boulder, and escarpment. But the most challenging thing is the drainage. As can be seen from the picture, the catchment area of the mountain is very large, and the water needs to be discharged to the valley floor through the whole reinforced soil structure. The abundant rainfall and the groundwater also need to be considered. Therefore, in addition to the structure design, we also need to consider a drainage system. We have designed several sections, and you can find the soil properties here. We use the site-owned material and the slope fill, which is a mixture of the soil and gravel. The phi- value is 27 degrees and the C- is 0. For the wall fill under the water level, we use the high-quality gravel, and the phi- value is 33 degrees. The construction started. As you can see from the previous slide, a small concrete foot foundation is designed. So now they are making some foundation treatment. And the construction of the lower part, which is a retaining wall. The wall has been designed using the Botechnic method in the software. It used the modular block as the facing. The project site is very far from the city, so the blocks were produced on the site by the contractors themselves. They used the precast blocks with a short length of geogrid inside. Then the short length of geogrid was connected to the full-length geogrid just using the bodkin. The drainageable soil were used as a wall fill under the water level. And there is round pipe were designed at the bottom. The construction of the upper part slope. The geogrid was wrapped around the blocks to form the facing. At each level, we use small steps to form the slope. This is more conductive for construction control. The tiers are 2 meters wide, and there is no grass seeds in the backs because it's easy for the plant growing in Yunnan province. And the drainage layer was set at the bottom of each tier. The grass starts to grow even the construction is not finished yet. When the slope is only 1 meter away from completion, the construction site was hit by unusual heavy rain, which lasted for a month and a half. You can see the water come out from the pipe and the drainage layer. The client worried about the settlement and the stability when they saw the water flowing. So they monitored the settlement for half a year, started just half month after the rainfall beginning. And the final settlement for the 30-meter high structure is only 4 centimeters. Now you can see the structure just finished. And 1 year after, amazing, right? For this kind of slopes, appropriate drainage system is much more important to suit for the local climate, such as the seasonal heavy rainfall, and you need to consider in the construction stage as well. In this project, we consider the catchment from the upper mountain and the mountain from both sides. We also consider the groundwater from the mountain behind and the drainage from the structure itself. So this slope can withstand the heavy rain for a month and a half. The reinforced slope solution saved millions of money in this project. The client was so satisfied, and 8 years later, they invited us to provide the solution again for their new crush station project. That's our case 3. The crush station is located on a hillside which is about 60 degrees. The vertical height difference between the transverse platform at the top of the crush station and the transverse silo at the foot of the mountain is 57 meters. The challenge is to build a high and steep structure in a narrow space and ensure the entire stability. We provided a steep slope solution around the concrete crush station. The maximum height is 33 meters with heavy truck load on the top. The slope is in 3 tiers and the face angle is about 65 degrees. The bottom slope is reinforced by anchors, which are designed by others. So we just assume the foundation is competent. The design parameters is shown here. For the high and steep structure, we normally recommend for the high quality fill. The main challenge of the project is the construction. The concrete crush station and the slope need to be built simultaneously. So there are a lot of interface processing, which is difficult, and the construction time is also very limited. But finally, we got it, a 33-meter high steep slope on the top around the crush station. The case 4, this is a landfill project in Beijing. The current landfill needs to be expanded, so a new dam is required. Both sides of the dam should be reinforced. The leached water level is only 2 meters below the top, and most important thing is that the seismic requirement. We should consider 0.2 G of the seismic acceleration. We designed the dam as a back-to-back structure. The outer slope needs to have a green appearance, and the inner slope we need to cover with a geomembrane. The whole structure is supported by the CFG piles, which are designed by others. The slope stability software is used to check the stability. We modified the whole structure, including the dam and the upper slope. The fill for the dam is gravel with a good quality. The load from the back and the top landfill have also been considered. Let's look at the these pictures during the construction. This is the matrix on the top of the files. It was stabilized with with a triaxial grid. And the slope construction again, and covering the geomembrane, and the finished appearance. Green in the outer slope and suitable for the geomembrane in the inner slope. Case 5, this is a slip slope repair project. The slope failed after heavy rainfall. It must be repaired in very short time. The problem is that the toe of the slope is very close to the house and the limited site is not available for the normal construction vehicle. So we have estimated the slip circle in the height of the slope is almost 60 meters. The design section and the detailed drawing is showing here. The slope was repaired just within 1 month. This is the final slope. The reconstruction for this kind of slip failure is very fast, just using the failed slope and reinforced by the gel grids in layers. You don't need to buy the high quality of the material, and the normal small construction vehicle is capable. In this case, it can save a lot of money. Let's go to the case 6. It's a project in Xinjiang province, which is in northwest China. They want to build a water station and then transport the water from a lower place to the higher platform. The maximum height is 37.5 meters, and 0.2 G seismic acceleration is also considered. We have designed different height of the slope. There are many details to consider about the connection of the slope with the water pipe. The construction of the slope supports the road to the top area so that the height varied along with the road level. And you can also see the big water pipe running through the slope. This is an aerial video of the entire project. The reinforced slope supports the whole operation platform. The project is 4 years now, and we have got very high praise for this slope. Case 7. This is a project in Fujian province 20 years ago. The slope needs to support a highway from Beijing to Fuzhou. It's located in a valley. There is a petrol station which is only 14 meters away from the pavement edge, and the petrol station cannot move. In this case, the reinforced slope solution is considered. The slope was constructed in 3 tiers. The height is 22 meters, and the face angle is 70 degrees. Sandy gravel is used as a slope fill. The slope uses wraparound facing, but a 2-meter-high masonry facing was constructed at the bottom of the slope as a safety measure against a potential hazard coming from the petrol station nearby. The soil bags were pre-filled with the topsoil and the grass seed, so that half a year later, the grass has grown and the slope has blended with the environment. Case 8, the project is a newly municipal road. It's very close to a residential area which is under construction. The original design is a slab pile wall, which is very expensive and the appearance is too ugly to be accepted. The new solution is a reinforced slope with a fixed angle 70 degrees. The height is from 3 meters to 12 meters, and the total length is about 120 meters. With this solution, the client saved 70% of the total cost combined from the slope construction and the limited foundation treatment. The picture shows the construction site and the final appearance. It has become the part of the landscape of the residential area, and people like it very much. The last two projects, I will talk about the back-to-back slopes. This one is an approach road to a natural gas purification plant. The road goes through the farmland. The maximum height is 20 meters, so the embankment is relatively high and the base will encroach into the farmland. To minimize the encroachment, the back-to-back structure was accepted. The drill grate was placed along the whole width of the embankment. You need to check the stability for both sides. The figure on the left shows that the slope stability was calculated using the Bishop circular sliding method. The photo on the right is an overhead view of the slope after it was completed. The back-to-back reinforced slope solution is much more convenient and economical for this kind of structure. The final project is a solution that is often used in the explosion-proof area. This back-to-back slope itself is stable, and the flexible structure surface can withstand the impact of the explosion, avoid the splash of the explosive, and also reduce the noise of the explosion. The picture shows clearly that the back-to-back structure can easily separate the working and living area. But most important is that it is cost-effective compared to the traditional concrete wall. And finally, I just want to talk something about the construction, because all of the construction sequence is the same in all cases. Here, you can find the foundation is ready, and you can place the first layer of the drill grate and the backs on the drill grate. The drill grate have 2 to 3 meters outside the slope. The backs were pre-filled with soils, and sometimes it will mix with grass seeds. Wrap the drill grate back over the backs, then pour it tight at the end of the drill grate and connect it to the upper drill grate with the bodkin. Construction machinery cannot travel directly on the drill grate. There must be a certain thickness of the fill. The large construction vehicle is used for the areas more than 2 meters behind the slope, and the small equipment is used near the slope. And it goes layer by layer. Please control the construction quality and ensure the smoothness of the slope facing. There are some more important details that needs to be paid attention to. The backs should be laid in same direction, and the drill grates don't need connections in the transverse direction, but in the longitude direction, the bodkin is necessary. Lighter compaction at the area near the face is very important. Otherwise, you can easily get the facing movement. And the drainage is much more important. Most of the failure were caused by the water. So there are some more pictures of the reinforced slope projects we have built. And if you have the safety design, careful construction, considering the drainage and the seismic acceleration, you will get a wonderful reinforced soil slope with very nice appearance. And that's all from my introduction. Thank you all for your listening. Thank you very much.
Okay, Sindy, thank you very much for presenting to us some incredible information and some very, very interesting projects. Now we have some questions. I've just been checking this. I mean, if you prefer, I can read them to you. I'm not sure if you can see them, but the first one isn't a question. So if we start here, we have from Ho Ming Chan to everyone, was to us. How do you manage the water level? Sorry? How can you manage the water level within such big slopes and when you have a big catchment area? So I think that was true in some of your projects. And is the control of water level in a small slope and a big slope, is it different when you have a particularly big slope?
Yes, correct. Yes, I think you are correct. That the water level in a small project and the big slope are different. And for the big slope, I think the important thing that you have drainage system.
Can everybody mute themselves, please? Hello. We can't hear ourselves. Could that person mute themselves, please? Can the organizer see who it is and mute them, please?
Yeah.
Okay, try. Yeah.
I will repeat again. So, correct that for the slope, for the small slope and the big slope, the drainage is different. So for the small slope, you just consider some simple drainage layer. So it's okay. It's at the bottom or and at the top, at the slope back behind the slope. But for the big slope, you need to connect all the drainage system together. You need to have a system. Consider all of the water coming through the rainfall structure. So you need to design and construct carefully to maintain the drainage system operate well.
Yeah, I think yes, I would also echo exactly what Sindy is saying, that design of drainage is very important, and especially thinking about runoff that was mentioned there and surface water, and then also internal water flows. If you're in a hilly area where you have natural groundwater flows, then you need to intercept them as well. So it's a major task and important to get it right. No, thanks, Sindy, for. Okay, so now from Phil Woodmansey, who's our chairman, he says, do you have any examples of vertical faces? Also, any slopes greater than 40 meters or work in areas of high seismic activity greater than 0.2 G? So three kind of questions in one there. Vertical, higher than 40 meters and greater than 0.2 G.
So for the vertical faces, we normally call it the retaining wall. So it's not the main topic of our presentation today. So I think maybe Mike will arrange another presentation talking about the retaining wall. But for the slopes, we don't recommend the vertical face if you use the wraparound facing, because it's not easy for the grass growing. So the appearance will be ugly. And the slopes higher than 40 meters. Yes, I think in China we have a lot of slopes higher than 40 meters, but I think the slope angle is flat. It's flat, so maybe the slope angle is lower than 45 degrees. So I think the design is simple for this kind of structure. And the areas of high seismic activity, I think yes. In Yunnan province and in Sichuan province, so you may heard that these two areas normally they will have the very high seismic activity. And in Yunnan province, sometimes we designed with 0.4 G. So yes, we have designed it, and we have this kind of pieces.
Yeah, no, yes, I mean, I think yes, you're right. Just on the vertical faces, people have occasionally designed vertical faces with vegetation, but I'd have to say, as Sindy says, it's difficult for maintenance and they look a bit strange. So it can be done if necessary, but one occasion when vertical faces are used with say wraparound is for temporary use. So sometimes you want to build a temporary structure. A vertical face with wraparound is perfectly okay. So yeah, it is okay. We now have a question from Kamim Al Kafid. How are seismic considerations incorporated into the design of reinforced soil slopes? And what role does a regional code play? So if you have a code of practice in your country, how does that affect this process?
Yeah, I think Mike, you are the expert in this aspect. So yes, we do have the standard or code, but I think the all design rules I think is the same. So maybe Mike, you can talk about on this one.
Yes, okay, of course, Sindy. Yes, I'd be happy to. Well, by now the methods for designing for earthquake loading are well established, but essentially what we do, we add additional forces which are there to represent the force from an earthquake. That is in what you might call the basic design approach. It's called pseudostatic because we apply a static load to model a very short-term seismic shaking. So it's not strictly correct. These days, if you want to, you can do full seismic analysis using finite elements. You've got to have lots of time to do that, though, because it takes a long time to build the model and then also a long time to run it. So if it's something that's very critical, then that's an approach. But the pseudostatic methods, I think, work very well in most situations, and those are the ones we'd have used for the designs in China. Okay, now we have a question from Willem. Willem was our previous speaker, and he was speaking about an earthquake as well. So Willem has a question here. Can you elaborate case 5 again? Please show the slides of the measurement of slope height. Thanks. Then he says, regarding earthquakes, seismic load, what is your seismic load, Sindy? So are you using 0.15 G or is there any limitation according to the Corps of Engineers? And what is the safety factor requirement for the seismic case? I mean, do you want me to answer some of that straight away, Sindy, and then you can perhaps try and deal with the elaborating case 5 if you want to find case 5?
Yeah.
Okay. Well, just sorry, Willem. Just so in general. Oh, hang on. I lost the question now. It's I've got to get it back. Here we go.
Sorry.
Yeah.
It's 5.
Yeah. Okay. So Sindy will find case 5 and talk about it in a second. So yeah. So well, we actually do design, Willem, for a wide range of seismic acceleration. We do tend to follow advice in the US codes. One important thing that you can, well, one thing that you can do when, if say that you have a PGA, peak ground acceleration of say 0.4 G, which is quite possible in some parts of Indonesia, then most codes of practice will allow you to use a reduced version on the assumption that the structure can deform. So if you can tolerate some deformation during or after the earthquake, then you can reduce to approximately 50% of the full PGA, which makes a huge difference to your design. However, there is one limitation on that, and that's if you are designing or looking at internal stability, where you're looking at sliding surfaces through the geogrid reinforcement, then it's not a very good idea to allow it to move a long way because the reinforcement will rupture. So for internal stability analysis, normally we don't make that reduction. But on the plus side, especially for polymer geogrids, their short-term strength is quite a lot higher than their long-term strength. So if you like, the polymer geogrids have a kind of a reserve of strength which can be taken into account during the very short-term loading from earthquakes. So they have quite some big benefit. In fact, that makes them rather efficient for designing these structures. So Sindy, a little bit about case 5. You've got it there?
Yes. So can you see my screen?
Yes, can see it. Yep, yep.
So
Yes.
this is case 5. So people ask for the measurements.
No, yeah, I'm sorry, I just jump in, Mike.
Yes, go on, Willem.
Yeah, the 4.6 is the reinforced concrete, yeah, isn't it? And then, but the slope failure still below it. So it's not the solution, or what? I'm sorry, Sindy.
Oh,
Just,
it's no. This picture, the wall is just the previous structure. So before it is failed.
okay, yeah, okay. And
Yeah.
then, okay, thank you.
Okay.
Okay. Right now, thanks, Willem. Oh, now questions have gone back
Thanks,
here.
Mike.
Okay, okay. So that was from Willem. Now from Ferdin Mangala, what are the benefits of using reinforced soil slopes in construction, particularly in terms of environmental impact and cost savings? Well, I mean, I think that's been mentioned several times, but I mean, maybe you'd like to summarize some comments on that. The environmental impact and cost savings. You mentioned that in most of the projects, but maybe you'd like to just summarize that, Sindy, for Ferdin.
Yes, the reinforced soil slopes. So I think it has many benefits. And first is because it's very cheap. You only use the soils and the geogrades. So the total cost is very cheap, and there's no other added loads from the concrete or from masonry. So the structure is relatively lighter than the traditional masonry or concrete structure. So in this case, the treatment for the foundation is much more cheaper. And the most important thing is that the reinforced soil structure, because you can see the plant or the grass growing on the face, so it's very implied to the environment. So normally people like it. So I think that's the main reason for the reinforced soil slopes.
Yeah, no, I think nice summary. I mean, it was very nice that in your example, Sindy, in both of those issues were coming up quite a lot. So I think, yeah, these are both very good points. I think one thing you mentioned there was being able to use available soils from your site. Because steep slopes not quite so critical on deformation as retaining walls, then we can probably use a wider range of soil types to build steep slopes, because if a 70-degree face moves slightly, you don't really know about it. So they are more, if you like, they're more friendly to lower quality fills than retaining walls. Willem's just got a backup question here. He says, Sindy, what province in China has seismic loading of 0.4 G, which you mentioned?
It's in Yunnan province, but just some part of the Yunnan province. So it's in that area that we normally get the earthquakes almost every year.
That's in the south of China then?
Yeah, southwest.
Southwest, yeah. Okay. Okay, that's all the questions in the chat. There's some very good ones there, and I think very relevant to the topic. Thank you for everybody who typed out a question. I don't know if anyone wants to ask a quick one before we ask our MC to bring this event to an end. But any last question from anybody who would? I know some of the people on the call today are very keen to ask questions. I know who they are, but I haven't heard from them yet. But if not, then I think I will hand back to Johanna, who will be able to bring our event to an end. So Sindy, can I personally say again, thank you very much for that presentation. It's a really wonderful summary of many of the issues to do with reinforced soil structures and just how successful they can be at dealing with these issues. And I mean, as you said, there are many more of them. You had 10 cases then? Yeah, 10. Although
Yes.
some of them were multiple slopes, like there were 13 in the first one. So in total, your total number of slopes in your 10 cases was quite a lot. I've seen some of them. I need to go and see the rest though that I haven't seen yet. So no, thanks again, Sindy, from me, and I'll hand back to Johanna to bring this to an end. And just to thank everybody who's attended. We have a very nice crowd of people online here. I hope you found that useful. The presented material will be circulated to attendees, so you'll get PDF copy of the material. So Sindy, again, thank you very much.
Thank you.
And Johanna, would you like to bring our meeting to an end?
Yeah. Okay. Thank you, Ms. Sindy, for your excellent presentation, and thank you also to Mr. Michael Dobie for guiding the webinar. Before we finish this event, please fill out the attendance form to claim your e-certificate using the following link in chat, or you can scan the QR code. For being a student, to claim your SAT points, make sure to fill out the attendance. Ladies and gentlemen, we have now reached the end of the event. Once again, thank you for your participation. We hope we can see you at the next event. At last, good evening and stay healthy, everyone. Thank you.
Thank you. Bye.
Goodbye.
Yeah, goodbye, Johanna. Thank you very much, and all other organizers. Thank you
Thank
for your
you.
help.
Bye.
Bye-bye.
Bye.